seminar this term, I believe it is. It's a pleasure to introduce Andreas Svedin. He did his master thesis in Uppsala in 2006 under the supervision of Bengt Gustafssons and together with Susanne Höfner. He then moved on to Columbia University to work with Ed Spiegel. And that was on a project which had to do with the solar cycle. The master thesis already involved time series analysis of AGB stars. So he was familiar with how to deal with time series and data that are a sequence of time. But there then arose this interest, of course, in doing something with the solar cycle data, because that's what Ed Spiegel has been working on with in the past. I would have forgotten the details if Andreas didn't remind me of some of those details. It was in the year 2009 that he was visiting us, and then again 2010 and 11 at least, where he was getting more interested in doing the time series analysis and wanted to do predictions. And there was a keyword which I mentioned to him, which is called data assimilation. And he had basically done something like this without actually knowing that word yet. Data assimilation is a term that is used in the weather forecasting business, and you will hear more about this from Andreas. But with that keyword in mind, he took off and did all the learning of what it actually takes to do data assimilation. He worked together with Inigo Malarossi here at Nordita at the time when I was somehow traveling, I believe, most of the time, and you were working with her. I remember all these email exchanges. But the rest of the story he learned from one of the students of Ed Spiegel's, namely Lenny Smith, who is at the London School of Economics. He's actually an astrophysicist, but went into economics. And he is actually doing things like data assimilation in a much more profound way. And one of the students, again, of Lenny Smith is one of his and our collaborators, namely Milena Cuela. And she is working at the City University in New York. So it's a collaboration between those three of us that led to the work that he is going to present right now. But it's just the beginning of something that can become a much bigger story. If you think of the sunspots here, that is this picture from Dan Schieselmann's latest picture in Physik Aktuell, you see that the sunspots are evolving with time, all the time. And at the same time, we might have, at some point in the future, a simulation which could look anything like this, of course, which would be somehow a numerical model of sunspots or the solar surface. If you now want to predict what happens, what you need to do is take a simulation which is reasonably close to the actual reality, but things are going to change. You just wait a few hours, and of course there's new convection cells arising, and of course new magnetic sunspots and force arising, which all need to be assimilated, as it's called. And what that actually means, he will tell us now.
Thank you.
Andreas, please.
Thank you very much for inviting me or letting me speak, and thank you for the kind remarks on Axel. So, you have all gotten the handout, I hope. It's out there somewhere. A few copies left. So, forecasting the future. Solar cycle 24 and grand challenges for time domain astrophysics. I think I started with predicting the future. We will actually get into what's the difference between a prediction and a forecast. It's actually quite important. So, to quote myself, a snapshot of the sky reveals little of the vast story of the universe that changes and evolves on all time scales. Only through studying the dynamical evolution of nature can we come to understand her past, present, and future behavior. That's my provocateur statement. So, let's first get to the take-home message, which usually comes at the end, but let's do it at the start so you know what to look for. There is something called data assimilation. It's good to know. It's basically the art of taking your reduced data and transfer it into something that a model can understand. So you can use it as the initial condition, or to compare with model output. And most of you have been doing this all week. I have been doing this all week, but we don't know that it's called data simulation. It's kind of nice to know what is this. And this is a vibrant field of research. There are actually PhDs in data simulation. They're doing this all the time. The weather people and the oceanographic people are really awesome at this. There's literature, mathematical theorems, there are programs, there are expertise. So we don't have to reinvent the wheel. When things get tricky, people have been thinking about this before. And it's nice to know that we can get help from them. So that's take-home message number 2. Take-home message number 3 is basically that. So with data simulation, with high-frequency observations, we are observing a lot of snapshots of the sky. And with state-of-the-art modeling, with Axel's nice observation, we are getting to a point where our observations and model can actually talk. And then we need to do the translation part correctly. And it can be complicated at times. And we can even start to get into the cool stuff of real-time prediction and anticipation of astrophysical events. That's something that maybe we have been dreaming or thinking about, but we are actually close to a time when we can do it, like predicting a supernova or something by studying the time series. Take-home message number 3. So take-home message number 4 is get to do with solar cycle prediction. And basically, this is a nice prime target. We have a lot of models, we have a lot of time series, and a lot of people thinking about it. So it's something that should be done. And also, there is this possible grand minimum that might be coming. You might have heard from Joanne Feynman last year that said there's some strange thing going on with the sun, and we might be entering a strange time. And we need to predict this to give actual decision support and so forth. So these are the take-home messages which you have on your nice take-home plate. So this is basically the solar cycle. It's an 11-year or 9 to 13-year cycle. The activity of the sun, it goes up and it goes down. When the sun is low, there's basically no sunspots, and around solar maximum, there's a lot of sunspots. And so what is extra nice with the solar cycle? We have time series that goes back to the time of Galileo, which is kind of unusual in the astrophysical field. That we have a lot of data, and we have and this is basically the sunspots that goes back. And we see here a number of interesting things. We have this 11-year cycle, and we have some kind of longer-term variation, and then we have this strange thing where nothing happened during the reign of Louis XIV, the Sun King. The sun was basically inactive. And we know that the sun was inactive. It wasn't sloppy astronomy that found this. When you look at the notes of Herschel and other giants here, they said, "Oh, I found a sunspot," and publish it. So it was a big deal of finding one of these few sunspots. The sun was inactive, and it might be doing it again. Short definition of the sunspot: this is an arbitrary thing. It's a measure of the number of sunspots and the number of groups, and it's weighted by the quality factor of the observer. And then you have a lot of different observers, and you weigh them together, and you get some kind of aggregated number. And there are different numbers, and there's a lot of discussion about the best way to calibrate this, but this is what we have, and we have a lot of people doing a lot of job to give us nice time series. But the sunspot number is kind of arbitrary, but it correlates to nice physical things like the 10.7 centimeter radial flux, the total solar irradiance, the number of solar flares, basically anything you want. So the sunspot number is an arbitrary proxy of solar activity. that might be seen from these plots by F. So we have the sunspots. As we said, we have the Maunder minimum and we have a smaller Dalton minimum here. But if you look at longer time series, this goes back to minus 10,000 years. It's 11,000 year time series from Vysotkin and Solanaki. And it's basically the gist is, if the sun is inactive, the heliosphere is weaker, and then you get more cosmic rays hitting the ice, generating isotopes, and you can drill down the ice and measure the isotope and indirectly determine how active the sun was. And here we see a lot of interesting things. The previous plot was about here, and we see these grand minimums showing up about every 200 years, I think the statistic tells us. And we also see that we are in a very high active stage, which is not comparable to about 11,000 years ago. So the sun has been very active and very long in this high state. So there are arguments, statistical arguments, that the sun should not be staying in this high state. It should go down, and because it has taken 400 years in the active phase, it should go into an inactive phase, because it should take about 200 years to go into an inactive phase. Also looking at solar type stars, we know that about 10% is in this inactive phase. So it should be due that the sun is inactive. Here we have some data from 1700. We have poor quality of yearly data, and then we have monthly data, and then we have daily data, and about from 1850 we have multiple sources, and here the data starts to get better. But if you have yearly data, it should be fine from about 1750, depending on. So what's the game? This is the solar cycle thing. This is from I think it's from the solar cycle prediction panel. And it's basically solar cycle 23. You're counting from 1750, I think. And this is solar cycle 23, and this is 24, and we're somewhere here. And the game is, you are here, and you should predict, is it going to be a high cycle or a low cycle? And this has implications for aviation and space flight, and the amount of shielding you have to put on your satellites, and you name it. So it's kind of a big deal. It's going to be low, and you have a lot of solar activity that's going to affect Earth, or high. And this is, of course, we have a small collection of different predictions from about 60 to 160, using a lot of different methods. I have some extra slides if you want to go into the details of these. But basically, what I wanted to point out is that the new thing for solar cycle 24 is that you have started to make explicit models. Right? You make a model and then you run a prediction. And this is when it started to get more mathematically sound. Here we are making rules of thumbs and so forth, and here we can actually go back and forth and see what works and doesn't work, and it gets more physics in here. A short note about how these methods has worked in the past, cycle 19, 20, 21, and so forth. And the benchmark is guessing the mean, that the next cycle is going to be the mean peak. And that gives you an RMS of 50. So if your method guess is about as good at guessing the mean, I guess you should do something else, because it doesn't give any extra value. The best methods are about a factor of 2 better than guessing the mean. If this is good or bad, I don't know. I think it's not very reassuring. So we are here at about 2013, and this is how it kind of came. The solar cycle 24 was very late, and it's somewhat low. There's a lot of discussion about this, and we can compare it to the prediction, and it's about the lower end of the prediction. It is the lower bracket of the prediction. But it's difficult to predict the future, especially make predictions, especially about the future. And you can find its citation by everyone you know and their friends, because prediction is difficult. So, what about solar cycle 25? The next one is coming. We are at a maximum, and the question is, what's going to happen with the next one? So we have this possible Livingston Minimum coming, and this is basically a measurement of the magnetic fields of the sunspots, and Livingston and Penn has been measuring this for a long time. And when they started here and they made a trend, it wasn't very appreciated, and they said that a linear trend can't be trusted with anything. And then it continued, and then it continued. And basically the argument is that if this trend continues and cuts a value of about 1500 Gauss, you can form a sunspot, because you need about 1500 Gauss to form a sunspot. So if this continues over multiple cycles, we can form sunspots, or form big sunspots. So this is an indication that has been going on for some time, that there actually is a trend that this activity of the sun is going down. I have some additional slides at the end with more different approaches that confirms this, that the solar cycle 25 hasn't really started. So a short note. Excellent that Druba came, because we're just going to make a short note of prediction and forecast. When I made this presentation, Druba said that I should differentiate between prediction, that I predict that it's going to be sunny tomorrow, or you make a forecast that it's going to be a range of 20 degrees plus minus 5 degrees. This gives you error bars, basically, on your predictions, which is what we really want you to do, and that also gives you better decision support if you put in the error bars. So prediction is basically a spot number. You say it's going to be 152. Here you say it's going to be a range, and this is the likelihood of it being about 150 or something. And this is the Merriam-Webster. So let's do a story of two masters. The first, of course, is Ed Spiegel, and it goes back to about the time when I was born, when Ed made a toy model of the solar cycle. And this is basically the model, and this is how the sun looks. Does it look good, or slightly good, or? I think it's still possible to see that this is the sun and this is the model, but it kind of looks nice. The second thing is that this model has an ability to turn off. So you have a regular behavior, and then at times it just turns off. So Ed made this model, and because he was thinking about the sun, and said, yeah, I have to figure out some kind of math that does this thing that the sun does. The sun turns off, so how do you do that in terms of math? So he invented on-off intermittency as a way of explaining the math. So he made this model. It's a 5-dimensional model, and it's basically a nonlinear oscillator where the amplitude is determined by a chaotic system. So as Ed would say, you have an oscillation, and the amplitude is tickled by a chaotic system, and when it reaches a threshold, the amplitude gets damped, and the signal goes away. So this is basically, you have the activity, and then it turns off, and you have activity, and it turns off, and of course it's possible to calibrate the interval of when it's inactive, or so forth. And this is the Moore-Spiegel chaotic system. So these three are tickling the amplitude. So Ed then said, okay, so if this math explains the sun, what is this nonlinear oscillator thing? So this could be the convection zone, fine. But what is this oscillator? So he thought about the ocean, and know that there is a layer in the ocean called the thermocline, which is some kind of layer between different zones in the ocean. And this is kind of oscillating. So I said, oh, it should be something like that in the sun. Let's call it a tachocline. It was probably an after-dinner joke that, of course, turned into something that was later confirmed. So this toy model was designed to describe the sun, and it also inferred physics, that there has to be some kind of thing that works like this. And that was the tachocline. So this is an example of observations turning into math that turns into physics, which is a not very common way of doing it. So I think that's an amazing thing. And the grand paper came out in 93, about 30 years later. And you have another paper by the same three people that discusses the technique upon our fingertips. So here we have the second master looking up at the old master. There is a match of, they are actually not looking at each other. It's just an illusion. Lenny Smith, a student of Ed, that about the time when I entered primary school, was speaking about, so we have a model and we have observations. How do we do this? It's really hard. And Lenny said, I'll fix it and come back. And that was in 15 years later, he came back and had solved it. So they were basically speaking about data simulation. So without knowing that it was called, or would be called data simulation, they discussed data simulation. So by public demand by Ed, I have included this quote from Wunsch, which says, a simulation is a term widely used in numerical weather prediction to describe the process of combining a forecast with current observation in order to update a dynamical model in preparation for another forecast. The term has more recently come to describe loosely any data model combination. Much of numerical weather prediction can be regarded as a form of engineering. Basically, you want something that kind of works, and then you figure out why it works later on. And this is one of the best explanations what data simulation is, because no one actually agrees or have a good definition. But this is a quote that kind of gives you the gist of what it is. So what did Lenny come up with? About, once again, 15 years ago. So we are looking at sequences in time. So we have a bunch of observations, these black dots, and we have some error bars, and we know that the truth is hopefully somewhere close to the observations, and this elusive true state of the system we can't really reach. But we have a model, so we can take any state or sequences of state. So we take a state and we make a prediction one step forward in time. And then we get some kind of error here. One-step prediction error or a mismatch. That the prediction of the previous step and the next step does not agree. That is something that tells you that you don't have causally connected states. So we can say that this is the mismatch. It's basically the sum of these errors. And you have a model F that makes a prediction of the next state, and you compare the difference between the next state and the prediction from the previous state. So this tells you the one-step prediction error, and then you sum over all the prediction errors. So what you want to do is you want to find another set of states at all times which is closer to a trajectory, more causally connected chain. So, as always, we set the first derivative to 0 to find the minimum of this function. And we do some differentiation of this mismatch, and we know that for this to be 0, it can be shown that this term has to be 0, which means that this term, which is the same term, is 0, which means that this term has to be 0, which means that for this to be 0, all terms has to be 0, which tells you that the only solution to this thing is when you have a trajectory of states. So the only way, and there's a global minimum, which is the trajectory of the model. Nice. So because we know it's a global minimum, we can do a gradient descent. Just walk down the gradient and find the minimum. And then you do an Euler approximation, and you basically get an iterative procedure of you start with a set of states, start with observation, and then you can make iterative steps to go towards trajectory of the model. So in a way, you're projecting a sequence of states onto a trajectory of the model. That makes sense. So how does this work? So basically you start with observations, and then you make iteration that takes you towards a trajectory, and it goes really fast. There is a number of iterations, and it is the mismatch or one-step prediction error. And we have the logarithm below, and we use this simple procedure, which we can use because we know that it's very nice. So how does this look? I hope you can see this. So we use a chaotic model. This is Lorentz 63. It generates, and we generate a true state, which is this blue line. And then we play the game, okay, let's do syntactic observations at 25% noise, which gives you these black dots all over the place. Then we forget about knowing the blue line and say, can we find the truth? And that gives us these red dots, which is scarily on top of the truth. So basically, our estimates starting from the black lines, we end up on the red. End up where we started. So this is kind of nice. The good thing is that typically in data simulation, if you have a long time series, it gets very difficult to compute. Here, having a long time series is an advantage because each estimate is constraining everyone else. So it basically forces it down very quickly onto a trajectory of the model. One thing that our mathematician friend have to tell us is why the trajectory that the method finds is typically the truth. We don't know that, but for some reason it conspires to actually land on top of the truth. It could be another trajectory, but it typically finds the truth. So we can also do this. We can do parameter estimation, which has been a long, difficult problem of how to determine a non-linear system's parameter, because a lot of the standard things like least squares assumes that you have linear systems and Gaussian errors, which you don't have. And then basically the whole theory breaks down. So here we have the true value is 8/3 or 2.66. And our estimate basically finds that the smallest value of the mismatch is lower here. So the best parameter gives the lower mismatch. So we can find parameters, nice. Now we get into the really fancy stuff. If we have the sun and we observe the sunspots, and you have a model with three variables or 52 or 10 millions, and you only observe one variable, how do you transfer that information into the other variables? You have unobserved variables. And this has been, if you speak to a statistician, this can't be done. This is statistically impossible because these are not correlated. So it can't be done. So what we do the same thing. We generate the truth in blue. We generate synthetic observation as one of the variables, and then we just throw dots in the other two in the general range. And then we use the black dots here to find the truth. And as you see, it's on top of the blue curve. So using information only from this thing, we can determine all three variables. And this has to do with things that our mathematician friends have to explain to us. It has to do with master-slave synchronization and other fancy math terms. But the nice thing is, so if this is, let's say you observe the surface of the sun. So you only observe, you have 10,000 observations, and your cube has 1,000,000. You can do the same thing. It is only a vector, and you observe some, and you assimilate the other ones. It's kind of nice. So how do we do this? Yeah, so basically we do a first thing of we hold on to the observations and take the unobserved variables and make them iteratively go towards the observations. So we make one step with the algorithm, and then it resets the observation back. So after some time, the unobserved variables are set to be dynamically consistent with the observations. And then we let go and basically find the true state of the system. And if you're really conservative and don't trust your model, which you shouldn't, you stop here and say, we keep the observations exactly as they are and only make the other variables be dynamically consistent. And stop here, and this is what you use to make your prediction. So, short note on time domain astrophysics, which you might have heard. So the question is, what nonlinear time series of signal are you interested in? And what models are you interested in to study in relation to the massive amount of data coming from PTF, Gaia, Loft, Kepler, LST, SKA? We're going to be drowned in time series. We're going to have huge data sets which we can start to use. And we have to connect this to models. And what astrophysical events do you want to predict in real time? This is kind of cool. So give me a model and a time series reasonably, and we can start to assimilate and turn parameter and make forecasts of astrophysical events before everyone else is going to do this. So we are at a time when we can kind of go into a new regime and try to test things. Because the best thing to test a model is if it can predict nature or make a forecast of nature, it apparently has some kind of value. And you can start to compare different models and sets of parameter, and this can give you back feedback on what models to trust or not, or what parameters to trust. So I guess you're curious about this also. So what is my prediction of the solar cycle? So this is basically, we take the sunspot number and transform it into a range that fits the model. And red is the solar cycle here. And we start at the beginning of the last 12 solar cycles. So here we start here and using all available data up until 1860 and make a prediction. And we do that by making an ensemble. We make 64 very close starting values, and then we just run them forward in time. And at times it's quite good, and at times it's quite bad. But the cool point about this is this can be argued to be a forecast. Here you actually use some procedure which is sound and self-consistent. This is done using the first model with standard parameters. So you can explore different models and different parameters and see what works and doesn't work. But this is, to my mind, the first solar cycle forecast ever made. And Ed thinks it's amazing. I'm not very happy about the details, but that's something to improve. And here we get to the picture which is on your sheet. This is a prediction that starts at the beginning of solar cycle 24. And we see some curious thing here. We get some kind of flat line. So if this actually means that the sun is going to go flat, probably not. But this is the kind of thing that we can do now and should do now, and now we only should calibrate parameters. We should go in a super computer and make this properly. And all the machinery is there, and we should just crunch it and make a prediction. And this is as fresh as it gets. So back to the take-home message. We have some extra features in the end if we have time. There is something called data simulation. If they say data simulation, it's basically this model data thing. And there's a full literature on softwares and expertise. You don't need to reinvent the wheel to use this. We can start to make real-time prediction of astrophysical events. It's kind of cool. And we can get on the bandwagon before everyone else. And the first place to do this is the solar cycle. A lot of people care about this, and if it's possible to show that we can do this, it's going to be a good test case, which we can apply to other fields or other areas of astrophysics. And even if the predictions or forecasts are bad, we need them, because a bad forecast is better than none, because the decisions report is still needed, urgently needed. So we need to improve the models and make it better and see what models work and what doesn't work. And eventually we should, of course, aim to make good predictions and accurate ones. So a short thank you to Ed, Milena, Lenny, Axel, Druba, Nordita, Columbia, Fulbright, Sweden American Foundation, Global Foundation, the people and the funding people. And if you want to know more, we have an excellent site called Living Review in Solar Physics, which is an updated site. And you have here a great article by Petrove about solar cycle prediction, if you want to know everything you want to know and more. And you have the long-term behavior of the sun with all the ice cores and so forth. We also have dynamo models of the sun. I didn't speak so much about the models of the Papi and Shanghori. You have them here. And the general way by Hathaway of NASA. And also, most of this work is published in Thesis, actually, by Lena, me, and Jude. They are working in different aspects. Here we basically look at parameter estimation. Here we look at prediction and so forth. And here we kind of try to apply it to a real case, not just a case computer. Fine. But we have some time for extra features if you want. One note. Most of the work assumes that your model is perfect. And if your model is not perfect, most of your assumptions that came into the algorithms break down. So if you want to do the proper thing of looking at stochastic models or models which are imperfect, you have to kind of reinvent a new way of looking at the problem. The good news is the machinery is possible to extend to those cases. It gets much worse in terms of how to actually interpret the result, but it's possible And that is one of the big advantages between our method and the flora of other methods available. That we can extend it to the non-perfect model interpretation, which is what you need to do if you want to do it properly. Some small extra slides here. This is a plot from Livingston. It basically tells, it connects the field strength of the solar cycle with the infrared intensity in spectral line 1564.8 nanometers, if you're friends with that. And you can basically see that it's possible to infer the magnetic field from this spectrum. Here we have the two features. The confirmation of the onset of the number 25. This is helios seismology, and basically you see the solar cycle 23 is here, solar cycle 24 is here, and we know that it should be that because we have solar cycle 23 here, 24 here, 25 should be here. It's not. 25 should be here, just as 24 is here. But it hasn't started yet. So the extended solar cycle, which starts before it actually seen, is not found using GARM. If you look at coronal measurements by Altrock, we know that there, about this time, there should be a rush to the poles. These kind of peaks that comes up. But with 25, there is no rush to the poles. Nothing happens. So we have three completely different solar physics measurements or studies that all say that there's something weird with 25. So there's something weird with 25, and we really need to go into prediction mode and see what's actually going on. And with that,
thank you. Yes.
Question, please. Made this interesting remark about the trajectory of states, which is an important consequence of your minimization procedure.
Yeah.
But you put that in context with the nonlinear data assimilation technique, I thought it was. But is that actually an aspect that is valid both for linear and nonlinear data assimilation? Or is that something new now?
So, one important note, let's see if we can find my slide. And the Lenny slide. So, there is a competing school called 4DVAR, which is used to predict the weather and everything else. It's a very nice method, but they are doing a kind of shooting method of, they want to find the initial condition here that gives you a trajectory all through this. So they are minimizing here. And that's very dangerous because it can go anywhere and you get a stiff problem. You have multiple minimas and it gets really messy. What we do is that we are looking at a sequence of states and we are going towards a trajectory of the model, not enforcing a trajectory of the model. And that gives you very different, that relaxes a lot of the constraints that causes a lot of havoc in classical data simulation. And as I said, if you are minimizing here and doing a kind of a shooting thing, if you have a longer time series, the constraints get coupled and it gets non-linear. And basically, what you try to do is finding a minimum of something that looks like this. And it's very difficult, and you get stuck in local minimums, and it's very difficult.
So the minimization of each piece in the trajectory of states is a common issue to all 4D bar methods, and not special to nonlinear methods. Is that correct?
So I think that 4D bar would claim that they are a nonlinear method, but it's based on assumptions and hopes that things are kind of linear. And there you have kind of the argument that if you look at a sufficiently short interval, then it can be kind of linear, and then everything should kind of work. But then you have a trade-off of having a short interval, and then you lose all the dynamics of the observations. So you want a longer interval, but then you can't solve it. So one of the main advantages, of course, is very high dimensional to work in n times whatever your state vector is. You are working in a huge state space, but you have a clear minimum which you just walk to. Instead of having a lower dimensional state, which is impossible to find a minimum.
So what I remember about nonlinear methods is that nonlinear methods take care of the fact that for the Lorentz attractor, you might have almost equally probable states which are, of course, very far apart from each other. Whereas with the linear method, you would always end up in the middle, which is certainly not an expected solution.
Yes.
Because they are really very distinct, of course.
And that's also a point of if you have a linear method, then you have correlations which are more clear. Here you can have a double T distribution.
Yes.
Which the classical methods it basically can't have.
Yes, that is.
There is another cycle you hear about, namely the Leisner cycle,
Yes.
which is about 90 years. Yeah, go ahead.
And last year, I think you had Joanne.
Which you saw maybe perhaps in this previous time series.
Yes.
I also do this one.
So the Gleisberg cycle is basically this thing. Goes like this and this. And I think that last year you had a talk saying that by Joanne Feynman saying that this thing is basically just a bump like this. And I think one problem that is basically taking the solar cycle and seeing it as a linear superposition of oscillations, which could be problematic if you think that this is not a multi-periodic thing, but a chaotic thing. So it could be seen what you philosophically think. Is the sun multi-periodic with very many periods, or is it chaotic? And I think could be seen as a point of view. But from my point of view, I think it's kind of clear that this is not superposition of things. And this gives you trouble. This gives you great trouble. Of course, you can have canceling of superpositions, but this gets very problematic if you see it as a multi-periodic thing. And if you look at this thing and say that this is a multi-periodic thing, it's more a feeling or a
carbon, yeah?
This is,
what is that?
yes, I think it's carbon, which is connected to substance.
And Any other questions?
Yes.
Yes, Dan.
Yeah, so if I understood it right, your grand forecast of the solar cycle, it was based on data up to 1860. And then the forecast started there. And since we are obviously very interested in the future, I wonder what's the cost of using all the good quality data now for the last 150 years and redo the forecast and see what will happen?
So it is not very much more expensive. So what we do here, let's say we do the 1905 cycle. We are using all data up until 1905 to make a prediction from 1905. So all these are made independently based on all the data available up until that time. So the later ones use more data than the previous ones. And it's not really, the time series are quite short. And this is done with yearly data, and even if we would do it with daily, the length of the time series are not the big cost. So we should be able to do it with monthly data if we would like, if it would make sense. It also kind of depends on, because our model here is kind of crude and it's only looking at, it's kind of approximate the cycle as kind of a single bump. Of course, we see that it's typically dual peaked. We are trying to make a model that makes this dual peak and try to see if that makes sense. It's kind of hard. I think it's possible, but we haven't found a way of getting the dynamics of the high, low. We also have some kind of me thing. And it might be able to model that, and then it would make more sense to use monthly data to capture this small scale of the behavior. But now we are basically looking at the peak value. That is what we are predicting and comparing with.
So in your case, the model was actually a low-dimensional model, yeah?
Yes.
Yeah. Of course, in reality, we should be thinking of a three-dimensional turbulence simulation of the actual sun. And in that case, it clearly becomes more complicated. We have three-dimensional states at all various different times, of course.
But the good news is,
not for data assimilation.
What?
Not for data assimilation.
the only difference is the size of your state factor and the size of your
Because your
computer.
observation is very limited, it's only on the surface. So if you use a three-dimensional model, then the whole problem is much less constrained. At most you should use a 2D mean-field model.
I mean, the model, we have also used as model tree, which can look into depth. So we do have three-dimensional information.
That is true. But
And
then
the actual model must be a three-dimensional one. Otherwise you don't get the sunspots, you don't get the convection, you don't get anything right.
But you are not looking for them.
Hmm?
You are looking for only the sunspot number per minute.
I'm not looking for that. I'm just looking for how the sunspots evolve. Does the sunspot split into a tube, for example? Does it
But that's
does
not
the
a
new
data
one emerge? Does
assimilation.
it submerge?
That's not a data assimilation problem.
It should be, why not?
I think that when the models get sufficiently sophisticated to answer these questions, and we have the observation. The good news is it is only a matter of the size of your computer. It is the same math, and we should be able to do this in 10,000 times 10 dimensional space. It's only a matter of the size of the computer. So it should be extendable into those kind of applications.
Yeah, right. And the reason is for the weather forecast, we have the same problem, of course. We don't have probes up in the air at all positions. We have it on a few positions, and you have much fewer positions in the ocean, for example, and yet you might have a few. So that's what data assimilation is all about. It can actually take care of these very sparse and inhomogeneous data.
Yeah.
Okay. Okay, if there's no further question, there's one question. Peter, please.
Yes.
Could you please put in a nutshell what happens? So you have the data, you have the model, and then you should be able to physically explain the model.
So what you do is,
Then you have the unknown parameters.
so what you basically do is data assimilation translates your reduced data into something that the model can understand. That's the basic line. You are making them being able to speak the same language to be able to be comparable. That's the first thing.
So you use the data to determine the parameters.
That's one use art. So what we do is we find the set of parameters that gives us the best fit in terms of the closest to a trajectory.
But when you create the model, do you think get the model from somehow physical phenomenon, or can you do it in a way that you just put in something and see how it fits, and then you consider later what's the physical meaning?
So you have two kind of schools here. One school, of course, is that you start with dynamo equations, and then you reduce it, and then until you find a model, and then you test the model. The other way of doing it, as I said, which is the edge school of doing it, the Spiegel school of doing it, is that you are looking at the observations and see what kind of math could explain that. But at the same time, you are thinking of physics. So you kind of make those things, you have the observations, you have the math, and you have the physics. And then you make a toy model, and then you see, okay, so what are these terms, these variables in terms of physics? So that's a different approach of doing it that goes from observations to math to physics. Or you do observations, or you do physics to math to be compared to observations. And once again, it's a matter of taste and style, and see what kind of works. The good news is we have a whole flora of models made with different assumptions and approaches, and we could just go through them and see which is best at predicting the actual sign. And if model A predicts 10 times longer, is apparently better at fitting what the sign is doing. So in some kind of objective term, it is better. So it's a way of evaluating which one we really can trust the most in prediction mode. I think is the hardest test of a model. I hope that answered the question.
Yes.
So we have time for more questions, of course, during lunch when we can sit together with Andreas and talk to him. But with that, then let's thank Andreas again.